Hi everyone, my name is Mohammad Saleh Vahdatpour from Georgia State University. Today I present our work titled Forecasting and Visualizing Air Quality from Sky Images with Vision Language Model. Our goal, uh, our main goal in this use AI to make air pollution more visible and understandable for everybody. Here is the agenda of today talk. We first talking about the introduction and motivation, then show our research objective, then talk about the our purpose framework, and we see our result, and at the end about the conclusion and future works. Air pollution means the presence of the harmful substance in the air, things like the smoke, gases, and small particles that we can't always see them. These pollutants come from both human activities like car and factories and natural sources like the dust storms and wildfires. They can make the air unhealthy to breathe and affect our environment, especially in big cities these days. PM2.5 refer to the very tiny particles smaller than 2.5 micrometers that can go deep into our lung and cause serious health problems. These particles mostly come from things like car emissions, factories, and burning the fuels. Nitrogen dioxide and sulfur dioxide are come from vehicles and industrial source. They can create a smoke and even acid rain. In this chart, you can see that the pollution level in the traffic zones are much higher in the urban area. Traditionally, air pollution is measured using a special instrument like gas analyzers and particle sensors. These devices are very accurate, but they're also expensive and require training operators, and their maintenance costs are high. Because of that, uh, it's hard to have a dense coverage with this instrument, and we can't place them everywhere we want. So we started thinking about the simpler and cheaper alternative for them. Something like that could we work anywhere without any expert, like forecasting the air quality directly from the sky images. Big cities face some of the worst air pollution problems. Big cities like Tehran, Beijing, New Delhi, Los Angeles often suffer from heavy traffic, industrial emission, and limited air circulation, especially in the winter season. As a result, we see the presence of haze, low visibility, and serious impact on both public sense and daily life. These conditions make it clear why we need better and more accessible way to monitor and visualize the air quality. If I want to talk about our main goal, as you know, our goal is to predict and visualize the air quality directly from the sky images. But in this way, we face some challenge. The first challenges we have, the pollution particles are very small, so we can't directly see them in the image. We have to analyze their visual effect, like the haze or color change. The second challenges we have is the different weather and lighting conditions. It's sometimes show like the cloudy sky looks similar to the polluted sky, which makes it harder to model to distinguish between the cloudy and polluted skies. And the third challenges we have is the data set. We need a large number of reliable data set covering all kind of the conditions, but so that this data set is still limited for us. Our purpose framework is designed in two main phases. The phase one is the current work, which focusing on predicting and visualizing air quality from sky imaging using the with vision language model. And the phase two will be our future extension, where we plan to add software FPGA code design optimization to make the model more faster, greener, and more efficient for real-time view. As you see here, this figure show the overall framework of our system. To start with an input sky image, which goes through the several processing models. First, we perform the feature extraction, combining the Gabor-based statistical description and deep visual embedding from the convolutional neural network. And then the system predict the air quality category, and this result is passed to the vision language model that generate realistic sky visualization for each pollution level. And finally, the output is presented in the user-friendly interface that allow people to compare real and generated sky senses. Our data set we use is included more than 5,000 labeled images collected from 8 different regions, each representing various weather and pollution conditions. Every image is paired with its corresponding AQL label and table of the pollutant measurements recording from the official monitoring station near the same location we captured the image. This pairing the table and the image allows us to build a strong connection between the visual sky pattern and actual pollution level we have in the image. As you can see in this example, the data set covered a wide range from the clear blue sky to heavily polluted areas, and we are still expanding our data set, adding new image from the different regions and conditions. Uh, in the pre-processing step of our images, we first extract the sky region from each image. Then we randomly crop 200 to 200 patches from that regions. And this crop help us to increase the amount of the training data. Even though the number of the full image is limited, it also makes sure that the patches are diverse and not repetitive. As you can see here, the overall pollution level is the same, but the sky patches look very different in texture and color. This variety help the model learn more robust visual patterns. Another challenge we have is in the data set is that the most natural sky images belong in the good or moderate air quality level. So the data is not well balanced. We have fewer sample for more polluted categories, and to fix this problem, we extract more patches from the images that belong to rare or unrepresented classes. This helps us make the data set more balanced and improve the model ability to learn all pollution level fairly. After pre-processing, the images are passed to feature extraction stage. Here we use a hybrid approach combining both statistical features and deep semantic features. First, each image convolved with a set of the multi-orientation Gabor filters to extract directional texture pattern related to the haze and the color variation. Uh, from these filtered image, we calculate the simple statistical description like the mean, variance, skewness, and quarters, and combine them into the global feature vector. As you can see here, the double represent change clearly when the pollution level increases. In parallel, we train a convolutional neural network on the sky patches images we have. To learn semantic, this convolutional neural network is learn semantic level visual embedding related pollution intensity. The CNN architecture acts as a deep feature extractor, capturing higher level color and texture relationship that the grabber can't fully describe this level of the features. And the combination of the Gabber and CNN give us both low-level statistical information and high-level semantic understanding, which make the classification more robust. And finally, these extracted features are fed into the classifier to predict the air quality category for each image. To make the result easier to understand, we use a vision language models to generate realistic sky visualization for each predicted pollution level. In this part of our framework, the system first generates a text prompt that describes what kind of the sky image need to produce. For example, other pollution level beside that one, the original image. At the same time, the original input image is analyzed by Blip tool to which convert its visual structure and content into the semantic text representation. This helps the diffusion model understand the real characteristic of the specific sense. Then the both system generated prompt and the belief to output are passes together to the stable diffusion model, which generate realistic synthetic image for all other air pollution levels. While keeping the same overall structure as the original image. So basically, the models show how the same image would look under different AQL conditions. In the last part of our system, we designed the user-centered interface that connected all models together. The interface allows user to upload the real sky image and see the predicted air quality level and compare it with the synthetic versions. These synthetic versions are generated by the VLM models, and each result is displayed with the AQL level, EPA color code, and a short safety recommendation for anyone. We also focusing on making the design clear and accessible. User can switch between the different pollution level and visually see how the same sky would look under each condition. In phase two of our work, we replaced the previous feature extraction and CNN model with our new hierarchical model, which integrates software FPGA co-design optimization. These models include two layers. The lower layer called the compact LLM model that perform direct equation solving for feature extraction, and this layer is run on FPGA hardware for fast and low power computation. And the upper layer is the adaptive LLM model handling the incremental learning and decision making, which run on GPU to adapt the continuously as a new data arrive. So this phase two represent the next generation version of our framework, more efficient in computation and more sustainable in deployment. Here you see some experimental result of our framework that the multi-feature CNN, which combined with the Gabber statistical descriptor with the deep visual embedding achieved the best overall performance around 90% accuracy. And as you can see, the synthetic images generated for each AQL level were reclassified by CNN with around 89% consistency and confirming the strong alignment between the prediction and generation images. which also evaluate visual realism using the standard metric that the SSIM score was point 0.8 and FID was 18.6, both showing the close match between the generated and real sky images. These results show that the or system achieve both accurate prediction and high level fidelity. We also run a user study with 12 participants that they show the VLM-based interface received the higher rating in clarity, intuitively, and the trust compared to the just text-only version of our application, which scored lower overall. This show the visual explanation make the system easier to understand and more trustful for users. In summary, if I conclude today's presentation, we present a vision language framework that predict visualize air quality uh, directly from sky images. The system combines classification and generative reasoning that make air pollution both measurable and visually explainable. This work bridges the environmental sensing and computer vision, moving toward more interpretable and sustainable AI system. In the future work, extending our framework by integrating software FPGA code design optimization for real-time and energy-efficient deployment. And also, we expand our data set, including the new regions and new all the conditions we have. And also, we conduct a larger user study to improve the interpretability of user trust we have. At the end, this work is supported by National Science Foundation. A special thanks to Professor Zhang and all collaborators who helped with this project. And thank you for your attention. I'll be happy to connect and collaborate. Feel free to ask any question you have and share your thoughts with me.